Okay, so let's continue with where we left in the last class. We briefly discussed about deep and strike, trend and plunge, and that we said is a part of the geometrical definition of structure. And we said that structural geology is mostly approached from three different angles. One is through its geometry, one is the kinematic approach, and the other one is the dynamic approach. In the kinematic approach, of course, we talk about how the deformation took place, uh, its displacements, the history of displacements, and so on. In the dynamic approach, we talk about the forces, and in the geometrical approach, we talk about the geometries, basically. That is what we see as a product of deformation. So, of course, we talked about scale and the importance of scale. We said that any geological features, when we photograph them, it's important to know about their scale because we don't want ourselves to be lost, whether it is microscopic, whether it is a mesoscopic structure, or whether we are looking at a regional structure. So scale is a very important parameter in case of studying geology, of course. Now, we will see that in due course that these few terms will keep on coming back to us, like continuous, discontinuous. It's mostly a geometrical definition of any rock body. We will see some definitions of homogeneous and heterogeneous. What do we mean by them? We broadly have an idea, but in terms of geological definition, how we look at them, and of course, isotropic and anisotropic, whether homogeneous and isotropic are the same thing, heterogeneous and anisotropic are the same thing. We will look into them. But these definitions will come back to us every now and then. Okay, so in case of scale, we will mostly investigate everything in three different scales: microscopic, mesoscopic, and macroscopic. So microscopic scale, which is typically we make some observation which is under microscope, be it normal optical microscope or be it scanning electron microscope, and that typically we are looking at structures which are less than 10 to the power minus 2 meter. And then mesoscopic, the scale which is essentially it can be an outcrop scale or a hand specimen scale. So 10 to the power minus 2 to 10 square meter, that is what we are looking at. And those sort of definitions, we will call them as mesoscopic structure. And macroscopic structures are generally field to regional scale. Of course, they are too large. Sometimes it is not possible to describe them in a single outcrop. And so you make certain maps and everything to actually visualize and understand the structure better. That is what we call as macroscopic or regional structure. Now, okay. So here you can observe the scales that we have been talking about. Say, for example, here you are looking at a very small scale folded biotite actually, a biotite grain which has been folded, and you are observing this particular structure under microscope. Okay, so this is a microscopic structure that we just talked about. This is a mesoscopic structure. This is a single outcrop. You can see the scale is around 50 meters. So you can stand in front of this outcrop and you can observe this beautiful fold that the rock layer has been folded. And these sort of structures which are described in a single outcrop, we call them as mesoscopic structure. And then of course microscopic structure, which are more than beyond a particular outcrop. So you make certain maps, and you have interpreted certain maps in your earlier introductory classes, but of course we will get into better definition of maps in the structural geology lab. But you can see that if these structures cannot be essentially restricted or described in a single outcrop, then we perhaps need to make certain maps and cross sections to understand the structure better, and that those will be the regional structures, right? Okay, so now what you can observe here essentially uh, uh, the importance of scale, first of all. So you can see here, here is a kind of set of layers, black and white, you know, and we observe that these layers are more or less horizontal. Yeah, their layers are more or less horizontal, and they look undeformed. I mean, as if they are mostly depositional sort of structure. Okay? And now, if we and our interest on structural geology will not be much in this domain, but although this has a certain geometry, but then of course our interest will be to look at this sort of structure where we see that loss of horizontality. You know, the horizontality or the layer cake pattern kind of goes away, and you can see that these rock layers have been kind of torn apart, have been bulged in places, have been narrowed down or restricted in places. We will see these are called boudinages when we proceed, but and we will see how they form. We will do mathematics around them, but these are the type of structures that we are interested in to look at in structural geology. So if we look at some more deformed structures, some more deformed field photographs, we will see. Say for example, you can see that this black layer, which was like a continuous uh, layer, now has been kind of sheared and folded here, you know. So something has happened which has kind of sheared this black layer. This is the type of structure we are interested to look at. Okay? You what you observe here, like this continuous set of white and uh, dark layers that have been kind of dissected by a vein-like structure, and near the vein, the layers are also disturbed. So we are, in general, interested in understanding such disturbances and what such disturbances, be it in the first picture and be it in the second picture, what do they actually tell us? The third picture we will explain later on. Let us move ahead. You can see here, of course, another example of deformed structure. You know, you can here also you could see some black and white layering, and then you can also observe that these black and white layering are not like they do not look undisturbed, right? They do not look horizontal. They have been folded, they have been torn apart. Some parts they are like thickened, some parts they are thinned. So some sort of disturbance is going on, you know. So there is, even if the layer is continuous, the layer is folded. In places the layer is discontinuous, that has been kind of dissected from each other, right? You can observe like a little bit of sleep that is also going on. I mean, this whole layer that has been a bit of slip. There is a sort of displacement along a line that you can also observe. Okay, so we are mostly interested in look at such structures where we observe, you know, such disturbances, and these disturbances we will call them as deformation. So if we now think about the three approaches that we talked about, okay. So the if we go back to this particular picture, so the first approach is the geometrical approach. So geometrical approach is essentially defining geometrically this deformed structure. Of course, that is the geometrical approach. Now, kinematic approach is to understand what sort of kinematics actually led to like a boring, monotonous black and white layer horizontality to transform to something which looks more intriguing and more deformed, more disturbed. So what sort of kinematics actually played a role? And to make that kinematics happen, to make that kinematic transformation happen, what sort of forces were actually responsible? And when we look into them, that is the dynamic approach. Okay, so the geometrical approach, the kinematic approach, and the dynamic approach, or the approach from understanding the forces, these are the three basic approaches by which you try to study structural geology. Okay, so homogeneous material, we know what more homogeneous material is. I don't have to, teach you what homogeneous material is, but then just to recap, the term homogeneous is understood as of uniform composition throughout, right? That's how we call it homogeneous. Or material composition and the properties are independent of the position. Okay, so now of course this is what you have to remember, that a particular material can be homogeneous in one with respect to one of its property, but it might not be homogeneous with respect to all of its properties, right? Say for example, a particular material can be completely made with quartz, okay, but then with respect to material, the material is quartz, but then it can have different crystallographic axes in different layers, right? So it is homogeneous with respect to one particular property. So when you say homogeneous, that means you are actually assuming that a particular material property is in your mind, right? And with respect to that material property, you are defining a material to be homogeneous or heterogeneous. So with the same with the same understanding, the heterogeneous material is of non-uniform composition throughout, right? Isotropic material means a material is the one which is uh, in which the physical properties are equal in all directions. Okay, if it is everywhere the directions are all equal, then we say it is isotropic, and in different directions, if the material property are different, then we call it an isotropic, right? We know about these things. Now, one thing you have to remember, that this is highly scale dependent. How? Say, for example, now we are looking at a sandstone in hand specimen in the left picture. You know. Now, if I just look at this one, and now if I ask you with respect to color or with respect to composition, do you consider this to be a homogeneous material broadly, or do you consider this to be a heterogeneous material? Can someone tell me? If I just give you, and it's not a tricky question, just by using your common sense, I look at the left picture of a sandstone, what would be your answer? Whether it is homogeneous or heterogeneous? Can some
Homogeneous.
homogeneous? Yeah, absolutely. I mean, there is no rocket science behind it. But then I take a small chip out of this sandstone, okay, and then I make a thin section out of it, okay, and look it under microscope. I hope you have seen some microscopic photographs before in your life, and you can see that the same material appears something like this. You have quartz. Everything is quartz there, but they have different colors. Under plane polarized light, due to different optical axis orientation, they have different colors. Now, if I show you this particular picture and ask you a very simple question, whether it is homogeneous or heterogeneous, what would you say?
Heterogeneous.
Heterogeneous? Yeah. So same material, if we look at it under a different scale, we might call them homogeneous, or we might call them heterogeneous. So scale is absolutely important. The one uh, at a larger scale, maybe this particular material appear as homogeneous, but if I look at it in a much more zoomed in version of that particular material, we will see heterogeneity coming along. Okay. Now, if we look at the next picture, I'll try to demonstrate. Now, if we look at this particular picture, okay, the first picture is of granite, and you can observe here different colors. Like these are like fleshy colors. Can you tell me what is that? What are the minerals present in granite? What is this fleshy color is from? What is the mineral? I taught you only in your lab class. What is that mineral? Someone has to tell me, what is that mineral? What is the basic composition of granite? What does it contain? Come on. See, this is one of the things that you have to think in earth science. Earth science is not like a discrete branch of sciences. So you have to have certain basic understanding about everything. Okay, so if I ask you the composition of granite by this stage, you should be able to answer me. So if I tell you the composition will be potassium feldspar, quartz, and some grains of biotite. Okay, that is what it has. Okay, so this fleshy color, this pearly texture, this fleshy color comes from potassium feldspar. Okay, potash feldspar as we call them. And then this whitish color that is coming from quartz, and this black color is perhaps from biotite. Okay, now if I look at this one, it will appear to you as inhomogeneous, right? It doesn't look like a homogeneous material. But then if I ask you whether it is isotropic or anisotropic, most likely, I mean, it is, I mean, if in a very sensu stricto definition, it is perhaps anisotropic. But then, broadly, it is an isotropic material. Now, what do I mean by that? If I take a single point and if I go like, 10 grains this way, 10 grains that way, 10 grains this way, 10 grains that way, and everywhere I will maybe encountering equal number of quartz and potassium feldspar. Okay, more or less equal number of quartz and potassium feldspar. So this is an inhomogeneous material, but it is an more or less an isotropic material, simply because everything is kind of mixed up together. Okay. Now, if you do a very proper what is that called, judgment on your measurement, maybe it will appear anisotropic. But broadly, if you count the number of grains in all directions, they will be more or less of same numbers of same composition. Okay, so that is that in that by that definition we will call them it is an inhomogeneous material, but still it is an isotropic material. But you look at this one, this is the granite gneiss. So this is an igneous rock, but granite gneiss, what sort of rock? And then this will be igneous, metamorphic, or sedimentary? Gneiss,
Metamorphic.
metamorphic rock. So what do I see? That this is the precursor rock. Granite is the precursor rock, and then I apply some sort of pressure and temperature, and from that granite I create something called granite gneiss. Okay, and what do I see? What has happened between this transformation? That these heavier minerals have actually segregated out and formed layers. Okay, now we see these light colored grains are like arranged in a layer, and then the black colored grains are like concentrated in another layer. Okay, and hence there is a gneissic layering that has formed within this particular rock. Okay, so this is the precursor rock, and by application of some sort of pressure and temperature, I have formed this particular granite gneiss. Okay, now if I ask you whether this is isotropic or anisotropic, now if I take a point here and if I go towards my west or towards my east, I will find only felsic material. In simply because felsic means quartz and feldspar. That is what I will find. But if I go from this direction up and down, what I will observe, it will be encountering more heavier material. So by the means of metamorphism, this particular granite has actually acquired anisotropy. So this is an inhomogeneous rock, as well as this is an anisotropic rock, simply because it has created some sort of layers. And now if I try to understand its physical properties in the directions parallel or perpendicular to the layering, I will observe different sort of uh, behavior. Okay, so this is my isotropic rock, inhomogeneous but isotropic. This is inhomogeneous but still anisotropic. Okay, could I make the point clear to you? Isotropic, anisotropic, homogeneous, inhomogeneous, how is it dependent on scale? Is this clear? And how is it dependent on your observation? Everyone?
Yes, sir. Yes.
Okay, very good. Right. Now, so as a structural geologist, these are the questions that you have to ask then. Am I looking at a deformed rock? How do I know if I am looking at a deformed rock? First of all, if the rock is deformed, it will deviate from its law of horizontality. You have understood and read about law of horizontality, that the rock layers do deposit horizontally. Okay, and there is this law of superposition, that the older rock is generally at the bottommost place, and the younger rock is at the topmost place. Okay, stratigraphically, right? So the law of superposition and the law of horizontality generally get disturbed due to deformation. So if I see a rock which is not horizontal, my mind should start asking question whether it is a deformed rock or not. Okay. What is the scale of the structure I am looking at? Whether I am looking at a microscopic structure, whether we are looking at a mesoscopic structure, whether we are looking at a macroscopic structure. Is the rock and deformation homogeneous or heterogeneous? Okay, we just talked about what is homogeneous, what is heterogeneous. And then the last question that you should ask, whether, last but not the least, I mean, this is one of the questions that you ask, whether the rock is isotropic or anisotropic. Okay, if it is isotropic, why it is isotropic? If it is anisotropic, then what brought in that anisotropy into that rock? Okay, in the earlier example, it was metamorphism. Okay. So what does a structural geologist do? Observe deformed rocks and explain why and how they ended up in their present state. Okay, as simple as that. You observe a deformed rock and then explain how. How means we are talking about what approach, kinematic or dynamic? Can someone tell me how? If I answer the question how, we are going to look at the kinematic approach. Right, the process by which the rock has deformed. Okay, and why is the reason? Is the forces. Okay, so observe the deformed rock and document the deformed rock with respect to its geometry. That means we are looking at a geometrical definition. Okay, and then when we are trying to answer why, we are looking at the dynamic aspect, and then when we are looking at how, we are talking about the kinematic aspect. Okay, so these are the few tools that we have. We have field observation, the tool of laboratory experiments, and then analytical and numerical modeling. We will see how these are done later on. Okay. So what does a structural geologist do? To interpret and define on the basis of scientific data complex interaction of natural elements, large scale in both time and space, large time scale, non-repeatable experiments. Okay, these are all non-repeatable experiments. Say, for example, if I look at a folded rock in the field, I will not be able to, unfold that rock, and make it horizontal, and then understand how it has folded. So we are looking at a non-repeatable experiment, at the end product of an experiment that has nature done for us. Okay, so it's our job is to essentially unreveal the story just by looking at the end product. Okay, that is what we are going to do as structural geologists. We will look at a geometry which is already deformed, and then we are going to undeform it in our mind, and then understand the processes by which that undeformed state has come to this deformed state. What are the steps that it had taken to do that? And what are the forces that were responsible in making sure that the process happens? Okay. So that is what we call geological reconstruction. So time is the limiting factor, of course. Extremely slow rate of deformation and very large scale. Solving jigsaw puzzle. So there is no initial picture. Some pieces may be missing. We will see them. Multiple phases of deformation at different times. So we have to decouple these deformation episodes. Okay. So the final product could be the product of 4 deformation phases that it has gone through, 4 different kinematic phases that it has gone through. Okay. And so as structural geologists, what we have to do, we have to decouple all of them from one another to understand the kinematic processes. Okay. So what are the approaches? There are different ways of studying structural geology. Okay, the first one is called direct methods, and there are 3 types of modeling that is done in direct methods. So geometrical modeling, kinematic modeling, and mechanical or dynamic modeling. And then indirect method, what is called analytical modeling. Okay, so we will see what all of them are. Slowly we will see, we will look at them, get some gist, and we will apply them slowly while we move ahead with the course. So geometrical or geometrical models, this is what we also call structural analysis or geometrical analysis. This can be qualitative or quantitative. So a 2D or 3D interpretation of form, orientation of the structure. based on the data obtained from field structure, mapping, and geophysical data represented by cross sections and maps. Okay, we will see what do I mean by that. Then kinematic model, this is also what we call as strain analysis, reconstructing specific history of motion displacement, and mechanical model or dynamic analysis, reconstructing the mechanical processes that resulted in the dog deformation, deals with forces, rheology, deformation mechanisms, etc. Analytical models are mostly hypothesis based, model derived. Additional data collections will be needed and compare with natural observations. Okay, we will see what are these things slowly. Okay, just hold on. So now let's first look at geometrical modeling. Okay, so let's try to be little more what is that called, interactive by doing these exercises. Okay, so let me ask any one of you. Okay, just answer me. What do you see in the left picture? What do you see? As a layman, I ask you, you are a geologist, you are standing in front of this particular picture. What do you see? Anyone? Let's be a bit more communicative.
Sir, layer.
Okay, you see layers. Anything special about these layers?
Sir, faulting.
Why do you say they are faulted? Where do you see faulting?
Uh, Actually, between those, let's say, there is a crack.
Okay, so let's call them then fractures. Okay, I mean
Okay.
faulting means more like a regional thing. Okay, faulting or fracturing. You see some fractures. What else do you see? Are these layers horizontal? Are these layers horizontal?
Sir, these layers are bending at a very sharp angle, making sharp angle.
These layers are make bends are bent, like someone as if there were a set of cards and then someone has kind of they were stacked together and then someone has bent them forcefully. That's what you see, isn't it? That's how it
Yes,
looks
sir.
like. Any other observations? Be wild with respect to your observation. Nothing is a wrong observation. If you are observing, you can talk about it. What else do you observe?
Sir, in the image, in the right-hand side, topmost corner, the
Mm-hmm.
layers are not layered anymore. Like these are like more
Absolutely.
crumbled up.
They are more crumbled. Okay. Anything else? Very good observation. What else?
Fold.
Sorry?
Fold.
Yeah, so that was already been covered. They said that this is like yeah, bent means fold. Okay, so you see, yeah, the same thing. What else? Are the layers having similar thickness? Are all the layers of same thickness, or they are of different thicknesses?
Sir, as we are moving down, the thickness is increasing.
Okay.
Like,
Now, if I ask you to follow this particular layer, okay, do you see that the thickness is constant, or do you see the thickness is kind of more towards this bent part, and it becomes thinner away from this bent part? Where this kink is, do you see that the layers are thicker? Is that a good right observation, at least for some of the layers?
yes, sir.
Yeah. So that is another observation. Okay. So all the observations that you made are actually valid, and that is what exactly a geometrical model is. So what you have to do, so when I observe a particular field photograph, or we go to the field and stand in front of the outcrop, what we do, we In detail, we describe or document the geometry. We describe or document the geometry. Now, the way that you have described is absolutely fine and exactly right. But as the course progresses, we will learn some technical terms by which we can define them more technically. Okay? But you are absolutely right. Someone said that yes, we see that as if there is like a fracture here, like a plane of discontinuity, and this part of the rock is more crumbled. This part of the rock looks different. Okay, so there is some sort of discontinuity going on in between, where this part, the character of the rocks here is very different than the character of the rocks here. Okay, that is number one observation. Number two observation, they are of course very sharply bent. Okay, they look like a stack of cards which has been very sharply bent. That's true. They are very sharply bent. The second thing, of course, you observe as you said, someone said faults. Yeah, there are some faults because you do see some displacement. You can call them as well fractures. You see there are a lot of such, uh, you know, slip planes through which the rock has kind of little bit slipped. You can observe here this particular uh, white layer has been slipped along this particular the black line. If you draw a black line here, you will observe some sort of slip. Okay, some sort of displacement. Okay, so there are plenty of fracture planes through which we observe displacement. Okay, here also you can see there are some displacements. Okay, observe here. You can see here, yeah, here through here. If you follow this layer was here, and after this red line, this layer has come here. So there is a sort of displacement. Okay, sort of displacement. Yeah. Now you can of course tell me here, because I have taught you already, what sort of shearing is this, dextral or sinistral? Huh? Dextral or sinistral? If I keep a ball here, which way does it rotate? Clockwise or anti-clockwise? Hmm? Come on, guys.
Anti-clockwise.
Anti-clockwise.
What sort of shear is it?
Sinistral.
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 Sinistral shear. See, you can make that observation here as well. Now, if I look in here, what sort of shear? Here also sinistral shear, isn't it? Okay. So so this is one of the technical term, that the rock has been sheared sinistrally. Okay. Such terms we will learn more. Of course, this is a sharp bend. We call them as kink. Okay. So that we can say that the rocks are extremely sharply folded. Okay. And then there are a lot of fracture planes where we observe sinistral shears. Okay. Now this sinistral term, of course, this sinistral shearing, this is definitely kinematic. Okay. Okay, because it talks about some sort of motion or movement. Now, if we just observe, so we can make a list of observations here. So we can draw a nice interpretation of this. We can draw a nice line drawing of what we are observing in the structure, and then we can make a certain set of observations that we have talked about, right? And that is nothing but geometrical modeling. Okay? You define the geometry of the end product. Okay, that is nothing but the geometrical modeling. Now let's look at another picture.
Excuse
Okay.
me, sir.
Yeah.
Can you, sir, in the sinistral fault that you showed, so it formed due to a kinematic, to say, process.
Yeah.
But we will consider this under the geometrical model, right? Because
Yeah, I mean, you can say, whenever you talk about sinistral, it becomes kinematic. Okay. Then you have to, you cannot stop there. Then you have to talk about why sinistral. Okay, so if you are only restricting yourselves to geometrical modeling, then you just say that there are some shear planes. Yeah, if you write sinistral shear, no one will kill you. But then, if you, the next step will be, of course, the kinematic modeling and explain why sinistral, why not dextral. Okay,
Okay, okay, sir.
and that we will learn later on. But let's, for the time being, if we just describe the geometry, draw a nice picture of what I am seeing is geometrical modeling.
Okay,
That's
sir.
about it. Nothing else. Okay. Now let us look at this particular picture. So there is a pen you can observe here. So that provides me the scale. Now in my earlier picture, did I have a scale? Did I have a scale? No, it did not have a scale. So this is a flawed picture. Okay. Whomever has put it in the internet, it's a flawed picture. It must have a scale. Okay. Always when you take photographs, it must have a scale. So this one, Hakon Fossen, he has put a nice scale. So he's a good man. So what I am observing here, of course, now if I look at so this, but this is the drawing of that picture, right? So this is what you are intent to produce after you observe it, right? So what I'm seeing a lot of black and white layers, right? And those black and white layers are actually kind of are not continuous, right? Is the first thing. They are not continuous. They have been dissected by a number of fracture planes, okay? And the fracture planes have, deep, kind of oppositely dipping. If one dips towards west, the other dips towards east. Do you see that? Plenty of such layers where we do observe this displacement. Like if I see here, this is how the layer is going, and then all on a sudden there is a displacement. Okay, we see that here too. You see that here too. Yeah, here is my layer. Okay, and then I see here there is a displacement. So some sort of displacement plane is there. There is a displacement plane here as well. You can see. Okay. So I can actually transform this whole field photograph that I am observing into a beautiful sketch where all the layers are drawn and then all the fracture planes are drawn too, and their displacements are also very nicely described. Okay, do you get my point? Yeah. So see this beautiful displacement plane that they have drawn. So if you, is this a complete picture? Perhaps not. If you spend more time, you can go into more finer details, and you can do even a better job. Okay, but that will depend on what purpose you are going to solve. Okay, so depending on your purpose, you will do your geometrical modeling, and you will describe the layers. Okay, so the geometrical modeling will, of course, contain a sketch, a geometrical sketch of what you are observing, and the second thing is, of course, your geometrical observations. Okay, you get my point, everyone?
Sir,
Yeah.
in the previous slide, when you were talking about the sinistral fault,
Yeah.
sir, won't it be a reverse fault? That small
Okay,
part.
that is that is something. You hold that question for the time being. Okay, it's difficult to answer at this moment. Okay, you are right. Generally, when you observe, this is a folded strata, right? In
Yes,
the
sir.
folded strata, you do generally observe reverse faults on. In that sense, you are right. Okay, but then there are more intricacies here. Now, if you look at this particular picture, okay, by definition, this is a normal fault. Okay, why? Because this is the hanging wall, this is the foot wall, and you
Yes, sir.
see this is where it dips, right? And the hanging wall goes down. Yeah, the
Yes,
foot
sir.
wall is up. So this is, by definition, it is a normal fault. Okay.
Yes, sir.
But if I look at this one, Yeah, by definition, this is a reverse fault. Okay, but there is things to consider. You know, you are not supposed to consider this layer as it is. Okay, you have to unfold it and see your faults.
Okay, sir.
There are more complications around it. Okay, so mm, it's a good observation, good thing to ask, but we have to wait for some more time and I'm sure after a few maybe 10, 15 lectures or so, you will be able to answer it by yourself. Okay, how do you categorize them?
Yes, sir.
Okay, but that's a great question to ask. I'm happy that you are paying attention to that detail. Very good.
Yes, sir.
Now, what I'm observing here as well is a seismic section. We talked about seismic sections in our solid earth geophysics side. You remember what seismic interpretation is all about. So seismic interpretation is nothing but geometrical modeling. Now, it can be. So this, the one that you are observing here, this is an uninterpreted seismic section that is produced by all sorts of processing steps that we have talked about. You remember the move out corrections, the migration and everything. Okay, after acquisition of the seismic data. And then the final step is interpretation. So seismic interpretation is nothing but geometrical modeling. Okay, so this is what you are observing, and as an experienced structural geologist, you are coming up with something like this, where I have put all the thrusts, all the reverse faults around it, all the normal faults, all the layers around it. Okay, and I tell you, this is not easy. Okay, people are paid millions of dollars to do this job. Okay, the ones who are working in the oil industry and work on such very difficult seismic sections and come up with geometrical modeling of such seismic sections, they are paid very, very handsomely. Simply because it's not only about drawing these lines have to make sense. Yeah. So how would you know that these lines are making sense, or you have just drawn some lines which are random and haphazard? You have to do something called reconstruction, and we will see what reconstruction is later on. Okay. So after reconstruction, there should be complete balance in your cross section that you have drawn. Okay. There must be a balanced cross section. Balanced means, all the geometrical rules must be satisfied. And because nature doesn't work haphazardly, doesn't work randomly. Okay, it follows certain geometrical definitions. So once you are satisfied with a reconstructed, beautiful, balanced cross section, then your interpretation will be okay. And based on your interpretation, people will drill wells, invest millions and billions of dollars, right? So geometrical modeling, in this particular, it can be as simple as the one that we have seen in the first picture or the second picture, or can be as complicated as this. Okay? And a lot of decisions in the oil and gas industry are dependent on such geometrical modeling. Okay? So, it's simple. We will learn all the tricks and tips later on as we move ahead with the course. And hopefully, if you all pay your good attention and everything, and follow the courses, be attentive, regular, practice what I ask you to do at home. Okay, you will be able. These will be not difficult. Yeah, there is nothing to mug up in structural geology. Okay, everything is logical. Everything is quantitative. Everything is you don't have to remember a thing. It's all conceptual. So you will be able to do this job. Okay, so please make sure that you pay 100% of your attention, and whatever I ask you to do at home, please do them. Then you will be able to follow. Okay, so now we talked about this, we will talk about it later on. For example, this is a particular model which has been generated in the oil and gas industry. This is nothing but a geometrical model again, where different layers, faults, and folds are drawn, and then their hydrocarbon disposition is drawn, and these are the wells people have actually put, and then do some dynamic modeling around it and see how the fluid flows from one place to the other. Okay? So that is also these sort of complex geological models, computer generated numerical models. The basis of them are still geometrical. Okay, don't be too afraid by looking at all the colors. They will be very easy for you when we do the actual job. Okay, but let's look at some of the interesting kinematic model. So of course, you cannot do a kinematic model unless you have done a geometrical model. So the first thing is to describe the geometry. Okay, the first thing is to understand the geometry, describe the geometry. Once you are done with your geometry, the next step is the kinematic model. Okay. Kinematic model is the process of understanding the steps by which an undeformed rock transformed into a deformed rock, the final definition that you are observing, the final geometry that you are observing. Okay. Now, this is a beautiful structure, and my master's thesis was on this particular subject. This is called porphyroblast rotation. Okay. And when I was a master's student, this was a very hot topic. Nowadays, people have understood most of it. So nobody keeps a lot of, there are not a lot of interest now. But in those days, it used to be. And I used to do a lot of analog and numerical modeling around them as well. Okay. So what we observed in a ductile shear zone, we will see what ductile shear zone again later on. Do you remember, for the time being, it's a zone of intense deformation, places where the intensity of deformation is extremely high. Okay. What you observe, that if there is like a rounded clast in the rock, that rounded clast actually rotates. Okay, because of the shearing, that rounded clast actually rotates. It doesn't only rotate. What it actually does, it actually like takes up all the rocks around it, and rotates along with. What do I mean by that? Say, for example, I have a bed sheet. Say, for example, I have two bed sheets. Okay, and within two bed sheets, I keep a ball. Okay, and then I rotate the ball. Okay, can you visualize that the bed sheets which I have kept on the top and the bottom, what would happen to those bed sheets? They will also wrinkled up, right? Are you following my analogy or not, everyone? Can you think of two bed
Yes, sir.
sheets and keeping a ball in between and rolling up that ball? Do you see that bed sheet also wrinkling up? Huh? Or not?
Yes, sir.
Yes,
Okay,
sir.
very good.
Yes, sir.
So think about that there was this like a ball, okay, and these layers are like the bed sheets, okay. Okay. So this particular ball has rotated, because of the shearing that this particular rock has gone through. It has not only rotated, what it has also done, that it has taken its surrounding rocks and has wrinkled them as well. And this is what we call typical porphyroblast rotation. Okay, and porphyroblast rotation, describing this particular structure, is geometrical modeling. But then just by looking at this, and these are called the tails of the porphyroblast. Okay, these are called the tails of the porphyroblast. Looking at the nature of the tail of the porphyroblast, we can say whether it is a dextral shear or whether it is a sinistral shear, just by looking at the disposition of these tails. Okay. Now, in this particular case, it is dextral shear, right? Because it is already shown of the rotation of the ball. Okay. But in the field, this is what you will be left with, right? There is no definition. I mean, whether it is dextral or sinistral. Now you have to look at the scale pattern and you have to say whether it is dextral or sinistal. Now, once you talk about dextral and sinistal, what you are essentially referring that I had like these layers, these black and white layers, and in between I had this ball, and this is my first stage. Second stage, I'm just doing very simple job. Of course, this will be a bit more complicated when we do the actual job, but more or less this is the same. And then these layers had like a dextral shear. This ball started to rotate, okay, along with the layers around it also rotated, and this created this beautiful tail pattern. Okay. Now, when I am talking about these 3 steps, I'm talking about the kinematics. Okay. So this set of layers have suffered dextral rotation, dextral shear, porphyroblast rotated and created this structure. This is the kinematic model. That's about it. Okay. Now, of course, you can date this porphyroblast. Okay, there's the third step. You can date this porphyroblast, and you can also talk about the rotation speed, with what speed this porphyroblast rotated. More, advanced study. And from there, you can talk about the amount of force or shearing that was going on during this time. They will be all, part of the kinematic modeling, but more advanced kinematic modeling, of course. But if you just describe the geometry of this is geometrical modeling. But if you say that there was a sinistral shear, and when you say sinistral shear, you are saying that these layers were horizontal initially. The porphyroblast was kind of kept inside, and then you have put it under dextral shear, and this thing came up. You are doing some sort of kinematic modeling. Okay, is that clear, everyone? बताओ तो.
Yes, sir.
Okay, very good. Okay, now this is the structure that you are looking. This is called a bookshelf structure. अभी तो सब कुछ नया नया लग रहा है. मतलब तुमने कभी porphyroblast rotation क्या होता है पहली बार शायद देख रहे हो, है ना? तो थोड़ा सा this will be a bit more alien and stuff. But when things will be into your hand, this is such a fun subject, man. I can't tell you. Structural geology is the most fun, because I should not say that, but it's really the most fun subject. It's beautiful, actually. Looking at the structures, when you go to the field, if they're boring layer and layer after layer, would it be fun? It's not fun. You have to be a sedimentologist and look them with your microscope and stuff, and then have some fun around it. But for a structural geologist, you look at these beautiful folds and faults everywhere, and so beautiful to look at them. The first time before I went to the Himalayas, I went for a field trip in the Alps. Okay. And first time when I saw Alps and their beautiful structure, I can't tell you how happy I was and how beautiful they are. Now there is a place near Interlaken. I know all of you have seen Interlaken in the Bollywood movies. That is where most of the Bollywood movies are shot. There's a beautiful something called recumbent fold of a calcite layer, and the calcite by itself is like very white, and that layer is folded on the mountain. For a layman, it looks, they cannot make out whether it's snow or whether it is rock or anything. But then if you are a structural geologist or a geologist anyway, and you look and appreciate that structure, that such folding has happened, you are just top of the world. So I hope you feel equally passionate like I do when you look at structures after the course, at least. Okay, anyway, this is called the bookshelf structure. Why it is called the bookshelf structure, I don't have to perhaps tell you. Like these beautiful rock slices. Okay, but we are looking under microscope, the scanning electron microscope picture, 500 micron magnification. Okay, you can see that these like you have stacked your books. You all have books at home, and you must have kept them like this in your life. And this forms like a bookshelf, like a domino sort of structure, right? And by looking at them, you can think that there is a slip. Okay, if you just describe this structure, you are still in the geometrical modeling domain. But if you are describing, now this is what sort of shear? Dextral or sinistral? हाँ, dextral है कि
Sinistral.
sinistral shear है ना? When you describe that, it's Now if you look at something else, this is sinistral shear, huh? But some other definition, what people have shown, that the overall there is like a dextral shearing going on. This is dextral shear, huh? Now why would the overall rock have a dextral shear, but this bookshelf structure will have a sinistral shear? When you answer that, that will be your real kinematic model. हाँ, समझ गए? Bookshelf structure में आपको sinistral shear दिख रहा है, but overall it is a dextral shear setting. वो क्यों हो गया? How is it possible? Okay. If you look at this porphyroblast rotation, some of the experiments that I did as well, we could see that if the porphyroblast starts to rotate, so क्या होता है? If you put a force on something, if this is like this and if you put a shear on this, this will rotate like this, Sometimes with such shear, it starts to rotate in a different way, as if you are cycling to go to the front, but the rings are moving in the opposite side. If that happens, why? It's a beautiful story around it. We will see them later on, hopefully. Okay, and this is again another kinematic model, of course. See, you can see large scale, beautiful faulting going on. This is what type of fault it is, normal or reverse? If I have taught you before.
The normal.
नॉर्मल फॉल्ट, ठीक है. तो किनेमेटिक मॉडल में हम क्या करेंगे? किनेमेटिक मॉडल में हम उसका किनेमेटिक्स डिस्क्राइब करेंगे, हाउ इट एक्चुअली चेंज फ्रॉम वन थिंग टू द अदर. ठीक है, टाइम है थोड़ा सा और, या फिर स्टॉप कर दूं? क्लास है क्या? नहीं है, पर 5 मिनट ले लूं क्या?
Yes, sir.
Okay, so ठीक है. So this is so kinematic model, what it does. This is a regional kinematic model. I'll just show you a video and then we will stop. This is a beautiful kinematic model. So this is the first step, of course. Is perhaps the kinematic model of the Himalayas. Okay, so how the Himalaya is actually evolving from step 1 to the final step. That is also a kinematic model. How the Indian plate essentially goes slowly towards the Tibetan plate, and the Tethyan sediment starts to be folded. How all the thrust is stacking up against one another. Okay, the whole definition that you do. So, a kinematic model would typically involve more than one sketches, because right, the geometrical model generally is involved with one sketch because that is where you are describing the final geometry. But in the kinematic model, you draw number of sketches, more than one sketches, more than one pictures. So one is at the first, how it was before deformation, and slowly with time, like this is 100 to 80 million years before time. This is 80 to 40 million years before time. This is 40 to 30 million years before time. This is 25 to 15 million years before time. This is 16 to today. I mean, so this is the present structure. So when you describe, so this is perhaps, if I just draw this picture, this is geometrical modeling. But then coming back from something which was completely undeformed to something which is deformed is called kinematic modeling. Okay. Now, dynamic modeling, is, of course, you are trying to understand the forces. Okay? And this is also what we do in our lab. If you are interested sometime, I will invite you to my lab and I will show you. You have to give me some time because I have to actually prepare the experiment for you. My PhD students have to prepare or come someday when they are experimenting. Okay, I will show you what do we do in. मेरे lab का videos मैंने मांगा था, but I will show you someday. This is from someone else. Sorry. This is what we do in a dynamic modeling. This is dynamic analog modeling. Okay. So what you do, you try to give forces. I'll just explain in a moment. Just have a look at it first. Okay. So here you see a series of layers, okay, which has been made in the laboratory, which is made with sand and glass beads, okay, sand and glass beads. The sand has been colored, and then some sort of force is being applied. Now, this force, you know, this is controlled force, okay, and then you create structure. Are you observing this beautiful structure being generated? Huh?
Yes, sir.
So this is what we call dynamic modeling, dynamic analog modeling. You can do such modeling also in numerical modeling as well. Okay, that is what we do in our lab as well. Okay, so this is the fun stuff. So if you type sandbox modeling in YouTube, you will see like thousands of such videos. Maybe this one is another one. See, this beautiful structure being developed. So you can do all sorts of experiments. Okay, create your own earth in the laboratory. So you know this. If I say that this is my final structure, okay. If I just define the geometry of this structure, I'm doing geometrical modeling. And if I am going from, you know, the first step and the corresponding steps, just describe how it is being done. It is kinematic modeling. And then if you become quantitative, talk about the forces that were responsible. So here the forces are being given by this plate, you know. Then we are talking about dynamic modeling, where we are talking about the forces. Okay, so that's where I wanted to end this lecture, and we will get into more, you know, dive into more things on structural geology in the next class. If you have any question,
Excuse me, sir.
yeah,
Yeah, can we that your model that you have shown us?
yeah,
Can we do computational modeling also?
absolutely. I mean, yes, the answer is absolutely yes, and it is done very much like a regular basis also in our lab. So it's like the physical model and the computational model, they are like done as complementary to each other. Okay, there are certain questions which you can answer better in a numerical modeling. There are certain questions you can answer better in a physical modeling. Okay, both of them are done parallelly. Yeah. And there are a lot of standard softwares which can be used to do such modeling. Yes. Anything else?
Sir, do we have a live interaction tomorrow as well?
See, I asked that question to DUGC. He could not answer properly. People do not. I don't think people have thought about it or have in asked that question enough to DOA. So what I will recommend that I mean if you are I will teach in the same time. Okay. If you are free, please join. If you are not free, you can see the pre-recorded lecture later on. Later on, if I understand that still this model is going on, that I have to give 2 lectures, 1 pre-recorded, then I will shift to that model. Does that make sense?
Yes, sir.
Are you happy with it, or you are in the complaining mode?
No, it's okay, sir.
Okay. ठीक है?
Yes, sir.
नहीं कभी मतलब I this is one of the things that I have that if you have something which you are not comfortable with, you are fine to tell me, huh? So we will adjust. Okay, because I don't exactly know how this how this how this time it is. Okay, that's why I don't want to take risk and keep it like all the 3 live sessions for the timing. But if later on they tell me that then you have to be generous to me and you don't have to complain that sir मैंने बताया था आपको कि 2 लेक्चर करना है, ठीक है, ऐसा मत करना है ना.
Yes, sir. Sir, if students have any problem later in the future,
हाँ
I
तो
will
बता
let
देना
you
मुझे,
know.
ठीक है.
Yes, yes,
So we will adjust accordingly.
yes.
ठीक है. Or this is also I don't know how it is as a teacher, if I don't get to ये तो